All right, we finally made it to the end of 3.2. We're going to do two examples, tying everything together with our analysis, our qualitative analysis, our analytic solutions, and wrap it up in a nice bow to prepare ourselves for the next section. We'll do a ton of qualitative analysis and look at different kinds of equilibria. So we're going to start by looking at this differential equation, dy dt equals b times y. And I'm not going to tell you what b is, but I am going to start by giving you the direction field. So here is the direction field. And we can see the straight line solutions. It's something that's a little hard to see, right? Is that, again, we're moving this way on this solution. We're moving this way on this solution. Okay. And my question for you is find the eigenvectors. How can we find the eigenvectors? Well, we know the relationship between straight line solutions and eigenvectors. Specifically, the whole point of an eigenvector is that they're like the direction of the straight line solution, right? Is that any vector here, and so specifically we could look at this vector if we wanted to. This is the vector 2, 2. Right? Anything along this line, the direction field must be pointing directly towards the origin or directly away from the origin, and we can see that right here. So we have one eigenvector already. And again, you could have your eigenvector be 2, 2. You could have your eigenvector be 1, 1. You could have your eigenvector be 3, 3. It just has to point in the right direction. And again, it doesn't matter which one we call V1 and which one we call V2. It does not matter. We can call them whichever one we want. Well, what's the other eigenvector? Well, with the same idea, right? We notice that over here, this seems to be the vector 2, -1. So we could have that be our second one. Right 2, down 1. It's our second vector. And again, even if the direction field is pointing inside, right? If these were going, oh, that didn't work. Right, if these were going inside, our vectors would not change. The lambda would change, but the vectors wouldn't change, which does lead me to my follow-up question is what do we know about lambda 1? Lambda 1 and lambda 2. Remember, if lambda is positive, that tells us something. If lambda is negative, that tells us something else. So notice along both of these lines we're getting pulsed away from the origin. Okay. So, and wait, hold on. Did I draw this correctly? I must have drawn this correctly. Yeah. Along both of these lines, we're going directly away from the origin. So what does that tell us about lambda 1 and lambda 2? They're both positive. So I'm going to give you another, all right, here's like question A. Here's question B. Question C is if I tell you what they are, so lambda 1 is going to correspond to 1, 1. That's equal to 4. Do I tell you that lambda 2 is equal to +1, what is the general solution? Remember, these eigenvectors and eigenvalues give us straight line solutions. Notice these eigenvectors are linearly independent. The general solution to a system of differential equations is going to be a linear combination of those two linearly independent solutions. So we use the theorem from the last page. And we're going to say our general solution is any constant times e to the lambda t. Let's do this one first. Times its eigenvector plus any other constant e to the lambda t times its eigenvector. That's the general solution. Any k will work. K1 and K2 are any real number. That is our general solution to this differential equation. All right. We could do some graphical analysis here, but again, this section's kind of long enough, so we'll finish with one final example. And we're going to go back to our favorite kind of example, harmonic oscillators. So we're going to consider a damped harmonic oscillator. And remember, the formula for that is the mass times the acceleration plus the damping coefficient times the velocity plus the spring constant times the position equals 0. Remember, the dot means the derivative with respect to time. So let's say we're looking at a mass of a mass of 1, a damping coefficient of 7, and a spring constant of 10. What are the units of that? We're not going to worry about it. You can worry about that in physics. Okay? I'm going to be lazy today and just focus on the differential equations. So we can find this, right? We can find y. But that's a big problem. So first, let's write this as a system. All right, we're going to find the solution. First, we're going to write it as a system. And remember, how do we do that? We say that y prime, or y dot, is just going to be this new variable times v. Usually this is how we're writing it. Velocity. Velocity is how position changes. Well, then how does velocity change? Well, dv dt, that's y double prime. Here, maybe let's rewrite this first, right? Mass is 1, b is 7, k is 10. Right, so solving for y double prime, because this is y double prime, that's going to be negative 10y. Let's change colors. Minus 7y prime, which is v. And we could write this with matrix form, right? What is our a value here? It's the coefficients. Coefficient of y, coefficient of v. Coefficient of y, coefficient of v. And then we have a differential equation system that's dy dt is equal to a times y. Again, where y is going to be the position and the velocity. We could check this by multiplying this all out. 0y plus 1v should equal dy dt. Check. Negative 10y minus 7v should equal dv dt. Check. So this is our system. So let's use this system now. Actually, let's look at we'll start with some qualitative analysis. Before we actually solve this system, because we know how to solve this system now, we'll just find the eigenvectors and the eigenvalues for this matrix. Let's pause and do some qualitative analysis. So if we go over to here and say, okay, let's put dx dt is equal to just y, and dy dt is negative 10x minus 7y. And again, I'm using the variables that this thing likes. We can see, let's look at the vector field first. Let's not look at the vector field. Again, this is the problem with vector fields. Sometimes when you have really long arrows, it looks very silly. Let's look at the direction field. All right, you can see what's happening. All right, things are kind of spiraling or curving down to the origin, which makes sense. A damped harmonic oscillator is a spring with some damping coefficient. Maybe it's friction or something else, right? It's going to oscillate less and less and it'll settle. It'll actually settle quite quickly. We have some cool simulations I shared in Canvas a while back. I should pull those up to show them. But yeah, it's going to be like boing and then stop. And this is how it's going to behave. Remember, this is the position is the x-axis, which we're calling y. The position is the horizontal axis, and the velocity is the vertical axis. So if this is our initial condition, right, we initially have a positive position and a positive velocity. The velocity is decreasing. Wait, that's kind of weird. That's, if this is the position, this is saying that for a little bit, it's not moving at all, which is kind of maybe an interesting starting case. But yeah, and then again, the velocity is decreased enough that the position now starts decreasing over time. All right, and no matter where you start, you're gonna see some interesting things. You might wonder about straight line solutions. Maybe. Let's see what we have. Okay, so let's solve this. So when we solve this, really, again, what we have to do is find the eigenvalues and the eigenvectors for this matrix. So that's going to be when AV equals lambda times V. Again, you can solve this system of equations. What you're going to get is A minus lambda I times V equals 0. We want non-trivial solutions. Non-trivial when the determinant of A minus lambda I, remember, you can write vertical bars for the determinant, equals 0. What is A minus lambda I? It's negative lambda 1, negative 10, negative 7 minus lambda. Right, you're just subtracting lambda on the diagonals. Remember that identity matrix. We need to find when this is equal to 0. We multiply this out to find our characteristic polynomial. That's going to be negative lambda times negative 7 minus lambda minus negative 10 needs to equal 0. That's the determinant. That's how we calculate it. And that's 7 lambda plus lambda squared. I should have said, by the way, hopefully you know the drill by now, but I should have paused and said, hey, pause the video, practice, work ahead, make sure we're getting to the same thing. Plus 10 equals 0, and we can rewrite that in standard general form. Lambda squared plus 7 lambda plus 10 equals 0. And that factors. I know I'm going through this quickly, but that's especially valuable if you're pausing the video and working ahead. So we're going to get lambda is negative 2. Let's call that lambda 1. And lambda equals negative 5. Let's call that lambda 2. And we need to find the corresponding eigenvalues, eigenvectors. Also, note that both of these eigenvalues are negative. That means if there are, and they're distinct. So that means we're going to have two straight line solutions that are both going towards the origin. Origin's I almost said stable equilibrium. We haven't talked about that yet. But all solutions are going to the origin, which makes sense. So lambda 1 we said was negative 2. Lambda 2 we said was negative 5. We need to find the eigenvectors. Remember A was 0, 1, negative 10, negative 7. How do we find the eigenvectors? They need to satisfy this equation. So we have a system of equations. 0x plus 1y is normally how we'd write it. But remember, what are our vector here? V is maybe a poor choice. Right? We're looking for the position and the velocity. I don't feel good about this, but one's a vector, one's a value. 0y plus 1v needs to equal lambda times y. Right? This is a system of equations. This is the first row of that system. The second one is negative 10y minus 7v needs to equal lambda times the second one. You can use x and y if you really want. And remember, these should be redundant. We need to always make sure these are redundant. What do these equations become? 2y plus v equals 0, and negative 10y minus 5v equals 0. Are these redundant? Yes. Always check. Multiply the top equation by negative 5, you get the bottom equation. Then any v and y will work as long as they satisfy this. So v just needs to be equal to negative 2y. So if y is 1, for example, v needs to be negative 2. We found the eigenvector for this eigenvalue. And we do it again over here. I'll go through that quickly again. Right, that is 0. It's the same left-hand side, right? The only thing that's different is the right-hand side now has a negative 5. We solve this the same way, move it over, make sure it's redundant. Is 5y plus v equals 0. Is that equal to negative 10y minus 2v equals 0? Yep, multiply by negative 2, you get the bottom. So anytime v is negative 5y, we have a solution. So our second vector is going to be y, can be whatever we want. Again, I like to choose ones, and I don't like fractions, but again, there are infinitely many eigenvectors that you could choose here. This is one of them. So, last step, what's the general solution? Well, we know that y of t is going to be any constant times e to the lambda t times its eigenvector, plus any other constant times e to the lambda t, it's linearly independent, and again, another eigenvector. That's our general solution. But really, we don't care about the velocity that much. We can always find the velocity. It's just the derivative of the position. Really, we just want to know what is the position over time. And that's going to be k1. We can ignore the velocity components. Just k1 e to the negative 2t plus k2 e to the negative 5t. And the velocity, you can see, of course, the velocity is just going to be negative 5 times this component, negative 2 times this component, which makes sense, right? It's just the chain rule, no matter what the position is. K1 and K2 are any real number. And if we had an initial value problem, like if I told you an initial position and an initial velocity, we could find out specifically what K1 and K2 were with an initial condition. So this tells us a lot of interesting things about this system. Specifically, right, we know we have the negative lambdas. We know the system's going to the equilibrium of 0, 0. We could plot these to see how things are changing over time. Yeah, I think we'll call it here for now. We also do know how fast things are decaying. Right, they're at least decaying this fast at a rate of e to the negative 2t, which is quite fast as a decay rate. It might decay faster, but if K2 is equal to 0, this is the slowest it could decay. But anyway, that's pretty much it. I think we've done enough in this section. Again, chapter 3 is pretty big. There's a lot of algebra, a lot of steps. I'm trying to show enough steps to give you some practice while also not wasting time. So going back and forth between, okay, pause the video so you can get practice, but also sometimes it's helpful for you to watch me do problems as well, trying to find the balance without having every video be 20 minutes long, because 20 minutes is too long for a math video. But take it easy. Please ask questions. Good luck. You've got this. Lots of algebra, but don't worry, we'll do more qualitative analysis in the next section. See you later.